Welcome to this session on the general principles of metallurgy. The very term metallurgy means metals, study of metals and alloys, and particularly when you look at metallurgy, you are looking at extraction, how to extract metal from the resources that are available around us. And normally we find metal locked in some forms in nature, and the study of metallurgy explores the best ways to extract materials from naturally available resources as ores or minerals. So this session is outlined as follows. We look at the chief modes of occurrence of metals. We look at the Ellingham diagram, which helps us to see the different metals, particularly the oxides, and how they are easy or difficult to work with. We will also look at some processes such as pyrometallurgy, hydrometallurgy, and ways of extracting material. Coming to the occurrence of metals, metals do not normally occur freely in nature except a few. Most of them are locked into compounds, and these compounds are mostly oxides and sulfides. And these oxides and sulfide rich compounds are the mineral resources, and these minerals themselves are mixed with other waste material or gangue material, and they are collectively known as the ores. So when we pick up the ores, we first have to carry out a beneficiation process where we enrich the mineral content before we can carry out the extraction process. So we know the hematite as the iron-rich ore, and bauxite as the aluminum-rich ore, and these occur either in a rich vein or in different places, and these areas become mineral rich belts, and where excavation for these minerals takes place. So if we begin with high grade ores, then the process to liberate the metal is cheaper. On the other hand, if our mineral itself is low grade, the ores are low grade, then extracting beneficiation becomes also an expensive process, and further purification also will become expensive. So what are the factors which influence metal extraction? This depends upon the method adopted to extract, and this will depend upon the purity of the metal, because based on the purity we have different approaches. There is also the energy requirement consideration which has to be taken into account, and definitely the cost of the reducing agent which is used to liberate the metal. So these play a role in deciding which process is used to extract the metal. And another important aspect is the position of the metal in the reactivity series. So in this slide we look at the reactivity series, which is listed here, right from platinum, gold, silver at the bottom, and calcium, sodium, potassium at the top. So this is the least reactive and the most reactive. The more reactive the metal, the less likely to be found in its pure or native state. Most elements do not occur as separate substances, but they exist naturally as compounds. So metals tend to exist as metal oxides as part of ores which are excavated from the earth, of course. To recover the metal from its oxide, the compound has to be split and the metal has to be separated from the oxygen ion. And this is where this reactivity series becomes valuable, because the amount of energy required to liberate the metal is in increasing order as you look at the most reactive metals. Consequently, it's harder to convert it back to metal. And metals high up in the activity series have more stable oxides than those which are low down in the series. So, what are the methods for extraction? The method used to extract a metal from its ore is guided by the position of the element in the reactive series. As we said, the metals high up in the series are strongly bonded into the compounds, and methods such as electrolysis is the only method which is possible to extract such material. And the examples are sodium, magnesium and aluminum, which are extracted using electricity. Metals in the middle of the series are less strongly bonded, and these oxides can be reduced by carbon to liberate the metal. Here is an example. Iron and zinc are classic examples. Zinc oxide reacting with carbon gives zinc metal and liberates carbon dioxide gas. Metals at the bottom of the series can be found in the uncombined nature in nature. They simply need to be purified of the unwanted materials, and we have the pure metal. When they do occur in ores such as copper sulfide, heating strong enough is enough to displace metal from its oxide or sulfate compound. The examples are copper, silver and gold. So, it's important to look at the thermodynamic consideration involved in liberating the material. So, thermodynamics helps us to understand what process is ideal or what chemical reaction is most suited to liberate a certain metal. And we also know which reactions are favored. The spontaneity of the reaction, this can be given by the free energy values of the reaction. And it also helps us to choose the most economical reducing agent among the available choices based on the energy associated with it. So, the criteria of spontaneity is that the free energy change of the reaction has to be negative. This is the equilibrium reaction, and you can see that it depends on the equilibrium constant K, and this is a ratio of the activities of the products divided by the reactants. So, for the reaction to be favorable, the delta G has to be negative, or in other words, the equilibrium constant has to be greater than 1. So, the free energy change is also given in terms of the enthalpy change and the entropy change, and for the formation of metal oxides, metal reacting with oxygen which is in the gaseous state to form metal oxide, the delta S will always be negative because oxygen is present in the gaseous state. So, if temperature is raised, then T delta S will become more negative. Thus, for free energy change increases within increases in the temperature. We can see this in the Ellingham diagram. Coming to the Ellingham diagram, this is nothing but a plot of free energy change versus temperature for various reactions, and as we saw, these equilibrium free energy change are basically lines for different reaction, and the lines are sloping upwards because of the entropy change and the magnitude of T which increases as you go to increasing temperatures. And we also see that these lines bend at certain points, and this is because of phase transformation, maybe from the liquid to the vapor or from the solid to the liquid state. So, each of these lines correspond to each of the reaction, and we find that silver oxide converting to silver and liberating oxygen is right at the top, and other elements like copper, iron fall in between, and at the bottom we have materials like magnesium oxide and calcium oxide. We will discuss this further in the subsequent slide. So, what have we seen from these Ellingham diagrams? We see that all metal oxide curves slope upwards. We see that if it melts or if it vaporizes, then we have a slope change, and we also saw that the curve which crosses delta G naught at 0, and above this delta G naught is equal to 0, the material can automatically decompose into the pure metal, and the material at the top were silver and gold, which we saw in the diagram, and also the electropositive metal curves are at the bottom of the diagram. Any metal will reduce the oxide of another metal which is above in the Ellingham diagram. This is because the delta G naught will become more negative at an amount equal to the difference between the two lines at a particular temperature. So, if we have another look at the Ellingham diagram, so what we are saying is, so if I have zinc oxide and if I have pure calcium, because calcium has a more stable oxide, its Ellingham diagram line is lower, so I can have an exchange reaction and I can reduce zinc from zinc oxide by reacting with calcium. So, because here is a differential, a delta G naught differential, which favors such a reaction. So, carbon is a very popular reducing agent, and let us look at some of the properties of how carbon can be used to reduce metal. So, this particular line, this red line here, is the metal oxide line, delta G equilibrium line, and this is of course the Ellingham diagram, because this is delta G naught and the other axis, x axis, is increasing in temperature. And if you look carefully, this green line, this is the delta G naught line for carbon to carbon monoxide reaction conversion. So, this line has a downward slope because the carbon monoxide is in the product of the reaction. And with this intersection here, we are able to see that above a certain temperature, the carbon monoxide line has a lower delta G naught value. So, this helps us understand that above this temperature, the reduction of the metal oxide is favored by reacting with carbon. So, this is an important conclusion. So, if you want to understand this better, all you have to do is get the net delta G naught value, which is the difference between these two lines, okay, as delta G naught of the carbon reaction minus the delta G naught of the metal oxide reaction. So, if this value is negative, then this reaction will be favored and metal oxide can be reduced by carbon. There are other carbon reactions also possible. So, here they are listed: carbon monoxide reacting with oxygen to form carbon dioxide, carbon also forming carbon dioxide, and carbon forming carbon monoxide. So, each of these curves are shown in the lines here. The green line corresponds to the carbon monoxide formation. So, this has a delta S which is positive, and therefore, the slope is downward because you have half a mole of gas here and 1 mole of a gaseous species. On the other hand, you have equal mole of gaseous species when you react carbon to form carbon dioxide. Therefore, this line is horizontal without any slope change. Carbon monoxide reacting to form carbon dioxide. Here again, we have more gaseous species on the left hand side of the reaction, and therefore, we find this curve to be upward sloping. So, when carbon converts to carbon monoxide, so whenever this is below the metal oxide line, okay, carbon is able to reduce the metal oxide. So, here is a metal oxide reaction. So, when the free energy of the carbon monoxide line is lower, so we are looking at temperatures above this particular point. So, this is where carbon is able to act as a favorable reducing agent. On the other hand, when you look at the carbon dioxide reaction, so this is the horizontal line. So, beyond this temperature, this reaction carbon dioxide can be a feasible reaction to reduce the metal oxide. Similarly, when you look at the carbon monoxide to carbon dioxide reaction, so which has an upward slope, so above this temperature, this reaction can be a favored option to reduce the metal oxide. We also see that all the three carbon curves meet at a certain temperature, which is 710 degrees centigrade. This temperature is important because below 710 degrees centigrade, it is CO2 which has the lowest free energy change, which so therefore, CO becomes the favored reducing agent below 710 degrees centigrade. But if you look at temperatures above 710 degrees centigrade, we find that carbon is the better reducing agent because this has the lower free energy change. So, it is time to put a question to you. Look at this Ellingham diagram shown before you. So, the question is, what is the lowest temperature at which zinc oxide can be reduced to form zinc by carbon, and what is the overall reaction? So, in this question you should know which is the line for the carbon dioxide reaction. So, that is this line which we have shown here, this green line, and you have to look for the zinc oxide free energy curve in the Ellingham diagram. So, zinc oxide is shown here. So, we can see that this is upward bending here. This is because zinc volatiles here from the liquid to the vapor condition, and you can look at the point of intersection. So, this point of intersection, if you drop a perpendicular, and all you have to do is read off the temperature from this axis, and you can say that beyond this temperature, carbon is able to reduce zinc oxide. And the reaction is as follows: zinc oxide reacting with carbon to form zinc in the vapor state because of the high temperature, and carbon monoxide. Here is another question: what is the minimum temperature required for the reduction of magnesium oxide by carbon? So, once again we have to look at magnesium oxide, and magnesium oxide is this particular line, and you can see that now the intersection of the curve is higher than 2000 degrees centigrade, and if you drop a perpendicular carbon monoxide line, you can see that the temperature is higher than 2000 degrees centigrade, and therefore it is very difficult to reduce magnesium oxide with carbon because of the high temperatures required, and you can begin to see why electrolysis is a preferred route for this metal. So, looking at electrolysis, this is the most powerful means of separating the bond of the metal oxides, but also it is the most expensive, and this uses a lot of electricity, and that is the reason why it is expensive. On the other hand, reduction with carbon or carbon monoxide, this is cheaper and than electrolysis, but on the other hand it is labor intensive, and also there is a lot of waste generated in terms of gases thrown into the environment, or gang material, slag, which is dumped into the land, and there is a lot of physical labor involved in handling these materials, and also there is a large amount of initial investment required to start this process. On the other hand, the materials which are lower, they are easier to remove. You can do that by just heating the ore, And if you are above the delta G is equal to 0 line, then you can easily make these metals into pure metals. Coming to pyrometallurgy, pyrometallurgy uses heat to extract the metal from the mineral, and here is an example given of heating lead carbonate to form lead oxide and carbon dioxide. Some minerals can be decomposed on heating into volatile materials which will vaporize easily and leaving behind the metal, and such a process is called calcination. And in some cases we also drive out the water of hydration which is present in the material during the heating. Heating a mineral so that it will react with the furnace gases is called roasting, and the roast product, if it is a liquid, then it is called smelting. If some byproduct of the roasting product doesn't volatilize easily, then a flux can be added to react with the non-volatile gangue to create a low melting waste product to separate easily. And this waste liquid is called slag. The slag separates from the molten metal because of the density difference and trickles down. So here are some examples of the reactions we have discussed so far. We have listed lead sulfide reacting with oxygen to form lead oxide, and this is forming a solid product. And here this is a pyrometallurgy process, and when you form a liquid product we call it smelting. And in another example, here again we are forming a liquid product, zinc oxide, and here is an example where a flux is added to remove the silicate waste and form a gangue material which floats up because of its lower density. Coming to hydrometallurgy, hydrometallurgy is the use of aqueous solutions to extract metal from its minerals. Gold can be extracted by this method. First of all, gold is dissolved in sodium cyanide. This is an aqueous medium, and the gold forms a complex in the medium, and this is leached out. So we have this pure gold cyanide solution, and from which, filtering out the impurities, we are able to carry out a reverse reaction and precipitate the gold. And this is how gold, even from very lean ores, can be extracted. Some minerals dissolve in acidic medium, others in basic, and others will require salt solution. Here is an example given where we have used an acidic medium, and here again you can see that copper forms a sulfate, and copper can be sulfate in the solution form can be removed, and then the reverse reaction applied so that copper is precipitated out. And here is an example where a salt medium is used to extract lead. So sodium chloride in an aqueous solution can form a complex, and this salt, the lead rich aqueous medium, can then be treated to extract the lead. So finally, we summarize what we have looked at in this session. We have looked at the chief modes of occurrence of metals, how some of them are freely available in nature and others are locked into compounds, and this we could distinguish based on the reactivity series. And we looked at the Ellingham diagram, which is basically a free energy change versus temperature diagram for oxide materials, and the placement of the lines of different metal oxides in this diagram helps us to determine the challenges, or how difficult they will be or easy they will be in terms of extracting the metal from the oxide, and what type of reducing agents can be used to extract the metals. We looked at pyrometallurgy as an extraction process, and we also looked at an example of hydrometallurgy process to extract material. In the next lecture, we will look at electrometallurgy more carefully and look at how this is carried out in practice, and we will also look at some methods